Okay, let's continue on the topic of sensors and instrumentation. We'll go to the the topic, yeah, bit by bit. First topic of the sensors. So for this first topic, we will talk about the introduction to process control instrumentation. So as we know that explained in the first video for sensors and instrumentation topic is that the general engineering system, it contains of the mechanism that whatever the engineering is doing, the activity, and then usually there is an actuators that will drive that mechanism. And in order to control that mechanism, then there will be sensors. Yeah. So it is actually I would say a feedback or control system mechanism. So it is very important that before we go to the sensors and instrumentation topics deeper, of course, we will talk about more about sensors and its instrumentation, but we need to see from the system approach where it is the sensors and its instrumentation belong to which part, so that we can understand it as a whole concept. And later when we want to discuss in details in sensors and instrumentation, we have a onboarding understanding about the whole system first. Yeah. So let's look at process control instrumentation. We'll talk about the objectives. What is the objectives that we will do for these topics? And then we'll talk about control system and process control block diagrams. This is very important to map our thinking, our paradigm into block diagrams. And then control system evaluation. How do we evaluate it to make sure the quality that we desire is being delivered? And then analog and digital processing, unit standards and definitions. Yes, engineering requires this. Otherwise, we're not discussing on the same page. And sensor time response. This is, of course, we need to know the time response of our sensor. First order or second order, is it fast, is it slow? So when we know that, when it is combined in the system, then the process control system, then we can allocate the necessary needed time, yeah, enough time. For example, if you are controlling a motor and then you are sensing the position changing, the position changes there. So if the sensor takes, let's say, less than 20 milliseconds, or maybe 20 milliseconds, but you need to wait for that sensors to be updated within that 20 seconds for you to make another command. If you are doing it like before the sensors is being updated, then the time response is not really allocated properly before we are making another command. And significance and statistics, of course, we'll talk about it later. So one objectives. So the objective of this topic is that hopefully, as soon as we finish this, we can draw a block diagram of a process control loop with description of each element. So at the end, as usual, usually I will give some case study or some problems to be solved. So in here also later, you should be able to actually draw a block diagram of a system and how to connect them in terms of process control loop. So yeah, like that. And then should be able to list 3 typical control variables. There are differences in some control variables so that we can understand how our sensors will come in later. And then describe 3 criteria used to evaluate the response of a process control loop, yeah? And define analog signal processing and describe the 2 types of digital process control. So from analog to digital, of course. Let's look at control system. There are 3 here. Process control principles is like a ongoing process, yeah, control. And then there is another one, servo mechanism. Servo means to follow, to track. So some actuating actuator activity that will follow a track or a target, yeah, forcing something to go somewhere, things like that. And then discrete state control system, because this is digital. Okay, maybe we should ask ourselves this question: what is the objective of control? Well, general speaking is when you want to control something, the objective, so that the thing that you want to control is to follow your own desire, right? So I heard somebody says that if you cannot control something, then you cannot manage it. So management needs control. But further, if you cannot measure it, you cannot control it. So the whole management, this applies to many aspects of life. So if you want to manage things, to manage some organization, you need to be able to make sure to be able to control it. That's why leaders are given authority. Authority is actually the ability to control. But how can we control if we cannot measure it? In terms of engineering, it's about sensing, measurement. Yeah. If we don't need to control any processes, do we need any sensors? Yeah, it makes sense, right? That you need to have sensors. You need to have some kind of measurement mechanism, measuring mechanism, so that we can control the process. What is the difference between sensor and transducer? Actually, I've discussed this in the previous video. For the sake of this topic, they are actually referring to the same thing, yeah. But I already explained that sensor and transducer is different in a way of what? Well, because transducer is more to like the energy transformation. So when we talk about sensors, it is sensing physical phenomena, physical changes, and then like temperature. And then when you use thermocouple, then there are some changes physically in that material that is the thermocouple. Or if you're using resistant temperature detector, RTD, then the resistance changes due to temperature. So physical and physical, but you are combining it with some instrumentation like a Wheatstone bridge, then transform the signal from physical to electronic signal, then it becomes a transducer. Basically, for lack of a better definition, then transducer is more complex than sensor, because it has some mechanism of transforming energy like that. Yeah. Let's look at definition of process control. So what is control? Is methods or a method to force parameters in the environment to have specific values or specific range of values, I would say, because you can also force that parameters to float or to fluctuate within some range. Yeah, that's control. And control system, all elements which are necessary to accomplish that control objective. Yeah, whatever your control objective is, so the whole system is actually to support that. And then basic strategy is logical and natural. So we are using our logical knowledge on that, and natural in a way that we want it to be running automatically, like natural. So it will just do it as it is commanded. In living organism, like our self, or the purpose of self sustainability or environmental sustainability, then we are talking about logic of control system to maintain temperature in a certain point, or for fluid flow rate to flow in a certain rate, and then energy, and so on and so on. In industry, it is the logic of controlling a system to achieve some production rate, probably quality, quantity, positional accuracy, temperature, humidity, and so on. So both of them are applicable, yeah, in living organism, in our daily life, and also in industry. And then basic objective is for process control principle is basic objective is to regulate, which is maintaining that quantity at some desired value. And this is talking about the name of set point or reference point. So we will use this a lot. Yeah, when I said set point, reference point is the point that we wanted the output or the control variable to be around, or exactly at that. Yeah. So whatever the external influences, whatever the disturbance, whatever the noise, then we would like to have it really at that desired or set point. If you look at the picture here, this is the a tank with some water flow in, yeah, and then water flow out, yeah, Q in and Q out, Q in and Q out. So in this case, if you look at the observe the things here, so this process can be done by just self-regulation. I will explain a bit more detail, but self-regulation means as you input the water, yeah, and then it will stay at a certain height or level of height. Of course, it depends on the size of the output or the debit of water being flowed out of the tank, yeah, Q out. Yeah, it depends on that. And also, we can have a human-aided control later when we can see, I'll show you the picture later, that it can control the valve. And automatic control is by means of computing that it will be controlled with sensors, actuators that will open and close the valve and maintain the level of a water tank at a certain point. So let's look at this for self-regulation. Yeah. If you see the, of course, just to mention that when I wrote down later figure 1.1, 1.2, 1.13, it means it is taken from the book that I mentioned in the class, Johnson Boch. Then 1.1 means it's chapter 1 and then figure 1. So the figure 1 in chapter 1. So you can find it there later. So like Q out is equal to some K is some constant, multiply this by the square root of H. H is the height of the water level in the tank. So Q in will be equal to Q out for what? For the level to maintain. Yeah. Of course, if the water is Q in is less than Q out, then we will know that basically no level. It will just be drained out directly. As the water comes in, it will go straight to the outlet. But if the Q in is more than Q out, then the level keep increasing. So for the level to be equal, then H, then the Q in, flow rate in and flow rate out should be the same. Yeah. So how to derive the constant K? Of course, it's something that is depending upon the all the value here that we need to measure. That's where we need also sensor. Yeah, I don't want to discuss further on that, but this is just to show you some self-regulation. Of course, when you want the water to be the water level to be less, then you just reduce the flow rate in, the Q in, and then bring it back to its value, which is equal to Q out. Then water will be less, but again, it stays there. Yeah. So that's how self-regulation means. So this does not provide regulation of variable to any particular reference value. So the desired level H can be any value as long as Q out equals to Q in. So it's depending. If you just stop the water in and then just wait the level to go down, and then when you see that the level is the required level, then you just turn on again the level the flow rate in. Yeah, the flow in. Yeah, so not the flow rate in, the flow in. Yeah, so this is the example of liquid level control in tank. Yeah, and human aided regulation. So this is, as you look at it, there is some valve and some picture of a person that is driving the valve to open and to close it. So if the man is standing there, he is looking at the level. Yeah, of course, this might be a problem. If the tank is very big, then error can be generated due to the side of the S is the side tube level as the control variable. So the level of the water is the control variable, while the valve is the controlling variable, the manipulated variables, yeah, where the human is actually trying to control that. So for human-aided regulation is provide regulation to a particular reference point. So the human is looking at the reference point, the level, and then it will just adjust the level accordingly. So use sensors to measure desired output value for sure, yeah. And then we can see that the actual level is the control variable. Please get in mind of this, because I need you to really be able to make a difference between control variable, controlling or manipulated variables, because control variables is the variable that we need to achieve and control. And then also output flow rate is the manipulated or controlling variables. You are controlling the outlet, yeah? You're controlling the outlet by meaning of changing the valve position. But the final purpose, the ultimate purpose that we want is the control variable, which is the water level. And valve position is the manipulating variables, yeah, by successive increment or opening, closing the valve, like that. Okay, as you look at this now, the third one is automatic control. So you can see that there is this, let me show you my laser. See, there are sensors here to sense the level of the water. Yeah, and then this is the level of, and then it is being fed back into the controller. So the controller know what is the level of water in the tank. And then the controller then will be, with that information, will try to give a command to the actuators here. Actuators will open and close the valve according to the control action being given to it. So by this, then it is automatic. You just type in, probably log into your computer and says that the level is this and that and that, and then you want to change it automatically. And whatever the disturbance is coming in, then this water level will try to be maintained at that desired point. Yeah. Okay. Right. Sorry. Okay. So automatic control, the machines, electronics, or computers replace the operation of human. And sensors measure the value of process output and convert it to proportional signal S. Yeah, I show you. Let me just go back. Yeah, signal S there. Yeah, signal S here. Okay, in U is the command. So convert it to the proportional signal S, and sensor output is the input to the controller. So it is being inputted to the controller. And then controller performs evaluation and calculation to produce output signal U. Yeah, that's the control output. And then control output is the input to the actuators, which then change the output system by meaning of changing the level. Yeah, so that's process control principles knowledge. Let's go to the second one, which is servo mechanism. I already mentioned that this is the type of control system for slightly different purpose than process control. Yeah, slightly different purpose, because it is like tracking or following, forcing some parameters to vary in a specific manner to follow variation of reference value. So reference value might change, or it can be the same, but it is like tracking it. Yeah. So like a robot arm is moving and taking it. Yeah. Rather than maintaining a position level like the one before in level of tank water, or level of water in tank. So this is called also tracking control system, like an industrial robot arm. Just like do a check-in questions, yeah? Think about this, because I'm not going to always answer it in here, but just have a thought. And is the driving of an automobile best described as servo mechanism or a process control system? Yeah, yes or no, and why? Yeah, think about it, and we'll discuss in class later. Okay, some discrete state control systems. So first is process control system, and then go to the servo mechanism. And there's discrete state control system. Discrete, by the name, it refers to digital value. Yeah. So concern is controlling a sequence of events rather than regulation or variation of individual variables. What it means is talking about a report, yes or no, exists or don't exist, it is here or it is not here. Yeah. Example: bottling held products. So many variables in here, each regulated by process control loop. Again, there is a control loop, but the sequence of events must occur in a correct order. So this is what happened to discrete state control system. So one sequence will lead to another sequence. Even one sequence cannot be done unless the previous sequence is completed or is done. So even trigger, this is what it is. So start, stop, open, close, true, false, on and off. So if you may say, this is like an on and off control. Yeah. So better suited to computer-based controller. Yeah, and we might use a microcontroller or PLC or PC or any other discrete state control system. Yeah, this is the example. If you look at this, maybe this is like a manufacturing system, and then the object will flow through through by means of conveyor belt, and then the object will pass a sensor. There is a emitter and receiver, light source and photo switch, and then this will be informed to PLC. The object has passed. Yeah, so maybe it is an initial information for the next action to be done. So based on discrete event, yeah, it's basically on and off. Yeah, and then what is event? What is event? Event is something that is happening really. What is happening? Yeah, event. It's an activity, I would say. So a sequence of event also one after another, and then it involves true and false, on and off, open, close, etc. Yeah. So let's look at now process control block diagram. This is again in the first objective that we were talking about today. This is for identification of functional elements and operation within a system. How we can connect them. You see, is much easier if we can look at I think my video is off. Let me just turn it on again. Something was wrong. Okay. Yeah. So identification of functional elements of operation. So this is how we can picture the whole system, and then classify them into subsystem, and then we can connect each of them. So we can see the functional elements, yeah, each element of the system. Okay, process. There is process here, the complex assembly of physical systems, sometimes called the plant, yeah, process or the plant. And then measurement, yeah, this is our topic, sensor, to measure. Conversion of variables into a corresponding analog or digital value of the variable. Yeah, performed by some sensors. It is done by sensors. And then error detector. This is the difference between the actual value and the reference value or the set point, and its polarity before any control action can be taken. So this is actually what we need to have. Basically, this is the input to the controller. So the controller knows what to do because there are some input about the error. And controller, yeah, evaluate the error. That's what I said just now. Error will be fed into the controller, and controller will be evaluating and determining what action is needed. Yeah. And final control element, the device that exert direct influence to the process, which is the actuator itself. Yeah. Okay, let's look at this example. Now, if you look at this, there is this process we call plan before, and then when it is doing something, then there is C is the control variable. Yeah, measurement is by sensor, and then it will be sent back to the. This is actually the brain. Yeah? This is actually the brain. Like I said in the previous last week video or teaching, actually this part here is the brain. Yeah, this is the microcontroller or PLC or PC, whatever it may be. Yeah, so it is fed back to that and then being compared to the reference value or set point, and then there is this error calculation, and then the controller will take that error and then decide to give a command to the control element. So this is it. Yeah. So if you look at it, constructed of elements, so elements being constructed, and control variable is C. That's the one that we need to achieve. Yeah. Measured value of control variable is B, yeah, because we need sensor to sense it and then transform it to the electronic signal so that we can check, compare with the set point R, yeah, which is error, R minus B. And then controls output signal is P, yeah, in this picture is P, sometimes we use U, yeah. And then P is the manipulated variable, yeah. This is actually the variable that we send, we use to control the control element, yeah? And then U is the controlling variable. So these are the names. So when you are actually reading some case and it contains these terminologies, then you should be able to check on this page, yeah? The block diagram is a generic term to describe the working process being controlled independent of particular application model to represent distinctive element connecting elements. So we are making separation or what shall I say, like compartmentalization of each of these elements and how they function and how they relate and how they connect to each other. And each of them is distinct, yeah? Second question, yeah? And do this, and this is like a not homework, but we use this and then we'll talk about it in class. Your homework, I would say homework. It's a refrigerator, yeah? Refrigerator control system. So define each block in there. How can you come up with all the elements? It's like you are taking parts out. What is what is connected to what. Define each block in terms of the refrigerator components. If you do not know the components, yeah, you can just look up in somewhere or browse the internet, yeah. Please try to do it. And oh, I have the answer here, actually is being covered. I'll show you in class later. Okay, this is another example, a block diagram. This is actually the to control the flow of some liquid, yeah. Flow pipe. If there's a pipe here, it doesn't matter what is the liquid, maybe vapor, maybe gas, I don't know. It doesn't matter. So this function, this block diagram, is to control the flow rate, I would say. Now, if you see here, on the left, here is the instrumentation to actually measure the pressure. So this is a pressure sensor, yeah. So P/I, it means pressure to current, yeah. So the pressure 3 to 15 pounds per square inch. This is the range of that. Maybe the smallest pressure is 3 and the highest is 15 psi, pounds per square inch. And then it is convert the sensor or the transducer, I would say, will change that pressure into current 4 to 20 milliamps. Yeah, this is the controller. And maybe we have already put the set point into the controller. And then when it is done, the decision is made, then it is sending again 4 to 20 milliamps. Maybe you ask your question, why not 0 to 20 milliamps? Okay, there's another homework. Think about it. Why not 0 to 20? Yeah, signal. Well, let me just tell you, because if you use 0 to 20, 0 is basically 0. 0, not sending 0 or not sending anything is also 0. So it can be misleading, yeah. But when you limit it to 4, then we know there is a signal, but it is the minimum or the lowest signal in microamps. So it is sending to the current to pressure converter, your I to P, and then changing it to 3 to 15 psi. So this is actually the actuators, yeah. So this is the block diagram later that you need to look at. Okay, and this is the real, I would say, the real block diagram. Remember before, the process is pipe and flow, and then there is a sensor. Sensor is being fed back. Again, this is the controller, like I said before, microcontroller or PC or what, and then control will control the valve, yeah, like that. So the signal flow from a complete circuit from the process, and then we measure it, and then we check the error detector, and then the control and final control element, and then back to the process again. So it is called a process control loop or feedback loop. Yeah, this is a process control loop or feedback loop. Okay, now let's look at the objective of the ET. ET, the R minus C. So ET is error, equals to R is reference, minus C is the control variable. So what we desire is error is 0. Even though I know in certain system this can never be perfectly achieved, but it can be 0 with plus minus some accuracy. Of course we can do that. But the idea of to get the error as small as possible. The system should be stable. Yeah, the objective system should be stable, stability criteria. If it's not stable, then maybe the objective control system is not achieved yet. And the system should provide the best possible steady state regulation. Yeah. Steady state. Steady state means the steady at the end. Yeah. Stable, and then also it goes to a certain point that is desired. The system should provide the best possible transient regulation also. This is talking about what? Before it is reaching the steady state, how the reaction here? Is it fast? Is it slow? Is it too much overshoot? Is it very slow, like that? Yeah, so that's the objective. The practical requirement also stability. Yeah, I mentioned before, we need to be stable, and also steady state regulation, and then transient regulation. I just mentioned it all together before on the previous slide. So again, ensuring stability, evaluating steady state response, evaluating the response to set point changes and transient effect. I just did that. Yeah, maybe I can just show you the how can I get rid of this? How can I change this back? Yeah. Hang on a sec, yeah. Just go back again. Okay, so this is the evaluating the response of set points. So let me just go to the picture, like here, yeah. This is the picture. If you look at, see the set points starting and then going up here, yeah. And this is the control variable, yeah. Control variable, yeah. And then how is it? Is it like that or is it like this? Yeah. So one of the things that we can do, and then gauging response. Is it the response is over damped or critically damped? Don't worry about this term. This is we study. You study later more in control engineering subject. Yeah, it means that for over damped or critically damped, there is no oscillation. Yeah, and then the settling time is good. How much is it from 10% to 90% of final state? And what is the maximum error? Yeah, within 4%, within 2%. It depends on our specification. And under damped, this is usually when there is a fluctuation. Let me show you the graph. Looks like this. Yeah, it means fluctuates. Yeah, fluctuates here. See. So this is when it is under damped. Yeah. Okay. Let me continue. So data representation. Let's look at data representation. First is analog data. Figure is on the right. So data is like a continuous line. It means the values are real values. Yeah, real values. So it means from 1 to 2, there are infinite numbers of points there. Yeah. So magnitude usually in voltage and current, smooth and continuous. It can represent temperature, speed, voltage, current, pressure, and so on. And there are some which is called linear. Linear means if we vary the input, the output will vary also proportionally. But for non-linear, not really. Sometimes when we, at one point, we give input and the output result in one point. When we increase the input, we are hoping that the output is also increased, but it's not the case with the non-linearity case. And also the second one is digital data, is about binary data, and we study this in our discrete mathematics, Boolean algebra, binary data, 0, 1, 0, 0, and so on. Of course, there are limited bits, yeah. Sometimes because we have maximum number of bits, and we have lost some information regarding smooth and continuous variation. If you see the picture here, yeah, the graph here. So why is it like stairs like that? Because it's actually when we reach, when the data is measured at one point, and then there is a sampling action at the next sample, then before coming to the next sample, then the value is just stays. Yeah, that's why it is like a horizontal line, and then before it is going up, we go when it is reaching the next sample, then it will go to that point, and then before another sample, it is go straight again horizontal. That's why it is looking like it, yeah. And then we use, of course, hexadecimal, and then we use ADC, analog to digital converter, or digital to analog converter for conversion. Yeah, and this is one of the picture of that. So we can go to analog, and then for ADC, analog to digital converter, the output will be bits, yeah, bit 1, bit 2, bit 3, and bit 0, bit 1, 2, 3. So there are 4 bits here to represent the value. So if my input is, let's say, 5, yeah, then bit 1 is bit 0 is 0, 1, 0, 1. So that's how it is, yeah. Let's continue. On and off control, yeah. This is most elementary digital processing. Yeah, talking about heating, cooling system at reference temperature T. Yeah, R is Ft, and then V is Fr, then Ve. The voltage equivalent to that is the some K value. V ref minus V. Yeah, so V is in there. So it's just an example, sorry. So it doesn't mean much, yeah, when I mention it. But okay, deadband. Deadband is a range wherein no action will occur. I will give you one example later. What is a deadband? Deadband means like it's dead. Band is range, I would say. So in this range, when you put something, nothing happens. Yeah. Hysteresis, yeah, this is the behavioral system. Is different at the same value of variable, but is depending upon whether it is going up or going down, increasing or lowering. Yeah, like when we increase some voltage, we give voltage current to some ferromagnetic material, and it will go up in a certain path. But when we take off the current, of course, it will slow down. It will cool down. It will the amount of flux density will be reduced. Yeah, so this is ferromagnetic material. Then, but it will come back not the same way it is going out. Hysteresis, yeah. Oh, okay. This is what I say before the dead band. Yeah. So if you look at the picture here, there is let me get my thing again, my laser. Yeah, cooler and heater. Sorry, cooler and. So this is actually a cooling and heating activity. This is not just heater. Yeah. So actually, when the heater is heats up, you turn this on. The relay is on, yeah, and then the temperature is being measured, and there is this R resistant to voltage converter, VRTD, and then going back to here, this is like a comparison. So VE now is equal to K times V ref minus V here, yeah. So this is actually turning on that one or that one. Well, on this stage, what happened is when the heater is already heating too much, yeah, so maybe the picture will be, temperature will be, yeah, something like this probably, yeah. So we can see that maybe going back like that, and then going here, and then going up like that. So the temperature will go down. Yeah. This is the temperature. This is the time. So at some point, it just doesn't do anything at the 0 stage. Yeah. So I'm going to have but I don't want to discuss that in problems 1.11, page 47 in the book. I will also use this case study also later in class. Yeah, I don't want to spend so much time in this recording. Okay. Okay, and analog control also talking about measurement like the one the picture before. So this is a controller. There's a controller here. Controller and the heater, yeah, and heater. So heating oven and temperature being measured, and then there is this VREF and then V reference, and then what is the V output feedback to the subtraction mechanism here, and error detector, and then it will drive the controller. These all are variables all variables are in analog, yeah, analog form, yeah. So this is allowing continuous variation of some parameters, yeah. But we can use this also combined with supervisory control. Now I'm introducing another name, supervisory control. So there is this control which are all analog in this case, and then I am putting some computers. So before that, so I'm using ADC to capture the data analog because I want it to be put in the computers. And when I have decided something to do here, and then send the signal to the analog. So I have to convert it again from digital to analog. So this is actually an analog control system. Now have a supervisory control. Now this is just one example because we can have all digitals, of course, yeah. PLC, and we have a SCADA system, which is the supervisory control data acquisition, which will control that. It doesn't mean that supervisory is always digital over analog. It doesn't mean that. I'm just trying to show you there is a term of supervisory control. Next, yeah, this early use before frequent failure of computers preclude in its use in actual control operation. In the beginning, yeah, maybe some quite a few failures of computers, but it is used to monitor the operation of analog control loops and determine the appropriate set points. Yeah, that's how easy it is later. A long time ago, when we designed a controller like a PID controller using analog control, then when we want to change the value of our controller variable, yeah, don't worry whether you understand it or not yet, but when we want to change the value of control, for example, the gain is from 2 to 2.5. It's not easy if we are using analog control. We have to choose the value of our resistor and capacitor, and they are not really flexible, right? But if you are using computers and to monitor it and determine the appropriate set points, it's easy for us just to put down 2.512, just enter it in your keyboard, yeah? So if the computer fails, then the analog still running, yeah? That's the idea of that point also. And we use ADC and DAC to read values and set new points, new set points. Yeah, like this. So this is now direct digital control, DDC. So without the analog control. So the measurement of the temperature directly go through measurement system and ADC to computers, and computers directly go to the AC and then to the heater. Yeah, this is DDC directly, okay? So reliable computers perform the control function now these days, replacing the analog loop. That's why we don't really use analog control a lot anymore. Even our cars are all electrically induced, electrically controlled. And use of software in the computer for the control operation, error detection, and the determination of action. Like smart sensor, we have smart sensor also. Sometimes smart sensor, it has already some mechanism that it can sense and then directly make a decision, yeah? Like microprocessor. And then smart sensor integration to create network DCC, yeah? We can look at the figure 1.7 in the book. It is having like a master and slave. So like as I mentioned before, SCADA system is the master, the supervisory, and then have so many slaves, yeah, to control them. And two standard foundation, field bus and Profibus. Yeah, this is talking about plug and play, ease of use interconnection. But we don't study it here, just to show you the bigger. So this is the DDC. Yeah, the picture, the one before it, I say cooler and heater. Remember, we'll discuss more about that in study case and how PLC is connected to them. PLC have an input and output. So everything is just crammed into what shall I say? One processor, one item, one component. Yeah. So the early type of discrete control function using relay logic controller, relay on and off, the one that I showed you the picture before with this, but with relay, remember? And recently, relay logic operations are performed by computer called PLC, Programmable Logic Controller. So it's like just switch on and off. Yeah. So a programmable logic control is an outgrowth on and off type control environment. In this case, the heater and cooler are either on or off. Okay, 5 units. Yeah, this is, I'm not going to talk long. 7 base units, mass, meter, kilograms, seconds, ampere, Kelvin, which is mole, and what else? Radians, teradian, and all that. Others are derived from that. Yeah, this is just to have as engineer, we must write down the units in every calculation, because when you write 7, what 7 what? Is it kilometer or is it centimeters or millimeters? Yeah, you must write that down. And analog data representation, as I mentioned before, we can have this. We can have this sensor to current converter here, I to V. Yeah. So in here we have 4 to 20 that I mentioned before, and then in here we want to change it, going to physical value in sensors and going to be converted to the electronic value. And similar here, some analog data representation is pressure and the voltage. The voltage to pressure, this is like current to voltage. Yeah. And one example, yeah, this is actually very simple. Let me just do this number 1, but you can try again number 2. Number 1 here, this is taken from the book, of course, 17, the problem 17 in chapter 1. Suppose a liquid level from 5 to 8.6 meter. So there is liquid level and is linearly, remember, linearly converted to pneumatic pressure from T to 15 pounds per square inch. Yeah. And the question is this: what pressure will result from a level of 7.2? How do we find out? How do we know that? And after that, the next question is, what level does a pressure of 4.7 psi represent? Yeah. So there is this level, and then there is this transformation to pressure. Yeah. Of course, a certain level will give a certain pressure. When you lower the level, then you lower the pressure. So it is the question states that it is linearly related. Yeah. So it means that we can find we must find first the equation that relate the level and the pressure. Once we get that equation, then we can just input the value of a level, and then input the value of pressure to find the level, input the value of level to find the pressure. So this is just actually using the old method, which is 2 points, which is 5.5 and 8.6, yeah, compared with 3 and 15, yeah. So let's say this is a y, yeah. Let's say this is a y, this is an x, like that, yeah. So remember high school thing, yeah. Y minus y1. This is the finding the equation, and y2 minus y1 equals to x minus x1 over x2 minus x1. So if I'm just putting, it doesn't matter whether you put x is here or x is there or x is here, it doesn't matter. Whatever you choose, the answer will be the same, yeah? So y minus y1, let's say put it, say y minus 3 over 15 minus 3 equals to x minus 5.5 over 8.6 minus 5.5. So quickly, I will just, this is quick, yeah? This is 15 minus 3 is 12. And then I'll just go this. Y equals to 8.6 minus 5.5 is 3.1. So I have 12 over 3.1 multiplied by x minus 5.5 plus 3. Yeah, directly. I have the equation now. Yeah, so what you do, next one, if the question is asking what is the level, what is the pressure of level 7.2, you just put the value there, which is Y, this is the pressure, equals to 12 over 3.1 times 7.2 minus 5 over plus 3 is just a calculator matters again. Yeah. Number 2, a control output, and then you just continue with the pressure also. Yeah. Number 2 is even better because it gives the equation here. You just input the value. It's easy. Yeah. Try it at home. Okay. And then analog data representation also can be looking like this: xt and then txyt inside and the black box, and then outputting yt. Yeah. Transfer function is actually what? Transfer function is describing the relationship between input and output. This is the transfer function. Yeah. And then static transfer function or response, I/O relationship when the input is not changing with time. In equation, it can be like this. Yeah. Q equals to K square root of P. This is just example. It doesn't really make sense. Example. Yeah. So dynamic transfer function response, I/O relationship when there is a time variation of the input. So there is static transfer function and there is transfer function with revert to time changes. Yeah. So they are the difference, but transfer function is transfer function. Yeah. How to relate input and output. When it is relating to time, then it will change as time changes. Accuracy. Okay, let's look at accuracy. This is to specify the maximum overall error to be expected from a device. So what is the maximum error? For example, you measure is 15, Pak, and plus minus 1% or plus minus 0.1. So if it is 15 plus minus, so the highest is 15.1, the lowest is 14.9, like that. Yeah, measured variable accuracy plus minus 2C, uncertainty of plus minus 2C of any value. Yeah. And then percentage of full scale, we can represent it in terms of percentage, not value. So if it is 5-fold, then uncertainty is you have to 0.5% times 5, which is 0.025. So it is uncertainty plus minus 0.025. And percentage of span. So this is the percentage of range capability. Yeah. So if it is plus minus 0.3% of span, 20 psi to 50 psi gives uncertainty of what? So you have to subtract first 50 minus 20, then multiply by 0.3%. Yeah, which is plus minus 0.09 psi. Okay. Or percentage of actual reading. So plus minus 2% of 2 is just what? 0.04. Yeah, so that's kind of thing accuracy that you need to use later when we are measuring something. Don't forget that. System accuracy. Yeah. So if we look at system accuracy, overall accuracy expressed in terms of accuracy of element transfer function. So the transfer function itself. So figure 1.2 is not the item. Yeah. So fault plus minus D4. Yeah. V plus minus delta V equals to, okay, the picture, maybe I should just put the picture here. Yeah, can be like that. Yeah. So V plus minus dV is equals to K plus minus dK times G plus minus dG. Yeah. I'm sorry, there is a difference here. It should be capital G. Yeah. Maybe when I write it down or transfer it, it maybe changes nature. This should be K, yeah, so that it is similar to our picture. K, dk, G, dg, like that, yeah. And then this is capital C also, and this is capital P. So later you will know it. I better change it now. Why? Because I might forget that, and then it will continue until the end of time. Okay, until the next meeting, probably next meeting, and if I don't change it the next meeting, then probably it won't be changing again after the meetings afterwards. Okay, so I got it here. Yeah. So so this is like a delta is referring to as the uncertainty, yeah, uncertainty of the system. So in block transfer function. Okay, so that's just the general of it. So let's look at number 6, a few more. It's quite a bit, but this is all the basic foundation before we go to the nitty gritty. First order, yeah. So first order sensor time. The time response is determined by the solution of first order differential equation. So if you look at here, if you look at there, that this is actually how the system is looking. Yeah, this is what makes the difference. Yeah, the response of that. There is t minus t0, which is delta t, divided by tau, which is the time response. So output is in error during transition from bi to bf. Yeah, one point to another. Time constant t tau is the sensor specific. Yeah, specific sensor. So 1 minus e to the power of minus t over tau is the fraction of total change in the output as function time. Yeah, as time passes by. Okay, so it changes in that. Where when t equals to tau, so is 1 minus e to the power minus 1, which is this. Yeah. Some of them call this this is the rise time. Yeah, this is the time constant. Yeah, time constant. Time to reach 63% of the final value. Yeah, and then the step input, the output reach final value after 5 time constant. Usually when it is like 3 time constant, it can reach like 95%. When 4 times time constant, it can reach about 98%. When 5 time constant, it can reach about 99.3%. Yeah. So the value of that, actually that one. So finally we'll get there, yeah, the value of that. Okay. All right. See example 1.15 when you are looking at the book later. Second order. Okay. This is, of course, we have differences to the first order. Step change or discontinuous change is input result in output oscillation. Usually, it creates pulse fluctuation. Not always, but when it is under damped, then it can recreate that. Yeah. So this is just a quick. I don't want you to think too much about this, but this is having the value of that. Yeah, there is some sinusoidal function, because sinusoidal function or cosine function is one that can create oscillation. So A is the damping function, damping constant, and F is frequency oscillation. Yeah, combination of sinusoidal frequency F and decay damping A. So that's and the picture looks like that. It can be this, yeah. I forgot to mention before what is BI. BI is when it is starting, and BF when it is finishing, yeah. So if you look at this, there is oscillation, yeah, like that. So that's a sensor time response. And then, okay, I guess we are at the end of it. There are 2 examples here that I want you to do on your time before we come into class. Just think about this after looking at the notes, looking at this. This is a case of water level tank. Yeah. So it's figure 33 from the book. Show a manufacturing process diagram. In this process, the following independent control requirements must be satisfied. So you must control the level, LSP, and then you must control the temperature, yeah, TSP, yeah. So this is level. This is basically going to LSP. This is going to TSP. And then there is a control flow rate, which is here, which is QSP. So make a block diagram, complete a block diagram. You don't need to you just put this picture if you want to copy or print screen and then put it in your Word and then just add the combination of block diagram in. So include blocks for necessary signal converter. Yeah, if there are some converter like before, pressure to current, so you just put it there, for example, like this. Yeah, so I to P like that, yeah, because it is coming from that. Just think about this and try that. And secondly, the question is this. This is a civil level control system again with closed relay opens and close, yeah, which is this. And this is driven by relay of that. And of course, the input is from here, level control. So this is the key. This is the catch. Input flow is not controlled. The relay closes at 6.4 and opens at 4.8. The level sensor has transfer function of that. VH equals to 1. This is the equation of that. Remember before we wanted to find the equation and we calculated on screen just now. So you don't need to calculate that, but it is given here. So find the value of K here, required to open the valve when the level reach 1.5 meter. So you must put into the equation later 1.5 and then find the voltage. And there is this VR, yeah, VR K times VH. And then the next question, what level does the valve close? And the next question is you are given Q1, Q2, and then Q out here. When opened, what is the period of the level oscillation? You know what is period? Period means it is open when it is high and close. Yeah. Oh, sorry. When it is open, it's going down. Open is going down. And then when the level is below what is defined already, and it is closed, so going up again. And then when it is too much, reaching the maximum, then it is open again. So there is this going up and down. So one period means when it is starting going down and then going up again. Yeah. What is this period? Yeah. Okay. I guess that's all for today, and we'll talk about more in class. Yeah. So do your best on some exercises there. See you. Bye-bye.